It's been a project long in gestation. I hope it behaves kind of like wine, but anyway, I decided to bring it out for a spin. So what's this about? It's a good question. If we look at Bayesian decision theory, this is going to be kind of a bad intellectual history, but so C. Savage writes these elegant axioms many decades ago, motivated by the work of Definetti. And then a huge chunk of work in Bayesian econometrics since then has been, how do you go from these savage subjective beliefs to something to a tractable paradigm to be using in practice? And so priors, they begin by these subjective notions that they're just supposed to be like revealed through some type of process to, well, we have to make this thing doable and practical. So we do things like conjugate priors for a while, and then we design priors, we experiment with them, we kind of see, it's not, this is a process that's a little bit more engineering than it is kind of thinking subjectively and magically these are the things that pop out. And so if you want to look at ambiguity aversion, robustness, and like that, it's important to go beyond the axioms. You have to figure out a set of tools that are tractable to do things with, and then look at this process. Are they really capturing what you want them to capture, and kind of in what way are they doing that? And so I kind of view that literature, the ambiguity aversion literature, the robustness literature, is kind of scratching the surface on this, going from some axioms to actually implementation in ways that are interesting, revealing, and useful. And this paper is very much meant in that latter vein, and that's so you should kind of keep that in mind. We're going to be writing down families of models in ways that are at the same time tractable, and we want to also see whether they're tractable and interesting. So that's kind of where we're at. So I like to think of the motivation this as through model misspecification, and I like to think that as the entry point into, or the motivation for being interested in multiple priors models, multiple model models, and models of potential ambiguity aversion. So when we write down a model, it's wrong. We kind of know it's wrong. If we knew how to fix it, we would fix it, but we don't quite know how to fix it because we don't know exactly how it's wrong. And the only way to confront that I know of is to kind of look at wide varieties of ways in which it might be wrong and to explore the consequences of it. I like to tell the story about the Money and Banking Workshop in Chicago, which I've been witness of for decades. And so I would go to this workshop, and people would be very, very proud of imposing rational expectations and have the elegance of the equilibrium construct, all of which is true. It's a wonderfully beautiful whole paradigm and construct that's been demonstrably successful. And then it would come to the empirical work, and there would be, in the last 10 or 15 minutes, and so you'd ask people, well, why aren't you more ambitious? You're kind of like just scratching the surface of the implications. They say, well, this is just a simplifying model, by the way. This is just some simple abstraction. We don't really think this is the real thing. And then you say, well, so what are the agents inside the model doing? If they're embracing without full confidence this simplistic structure, they're not very rational. In fact, they seem to be stunningly naive. So it's in some sense, the rational expectations paradigm with kind of models being simple abstractions of more complicated things is not a perfect fit. And so I find it interesting to try to push out of it a little bit and see where we can go. So the approach here is we're going to begin with a baseline model. I'm not going to call it the true model, although I'm going to kind of match it to data, so it's going to be empirically relevant. And then the question is, I'm going to put a bunch of sets of models around it. So one could imagine putting, these are going to be big sets. I could put priors over these sets, but as long as I have enough sensitivity over priors, then I'm going to be, it's going to make learning very, very challenging. And so we've done other work in which learning is on the table, and this work is going to be off the table because it's going to be too hard to learn about by construction here. But on the other hand, we're going to put multiple models on the table, and then the interesting question is kind of how we do that and how we think about that. Now, we're also empirically motivated. Our first stabs at doing this, when I first doing this research, we did these calculations, and we put arguably big sets of models on the table, but all the implications, the observable implications for financial markets, the kind of uncertainty prices and the like, had no interesting time variation attached to them. they were essentially constant over time. So it was not delivering time variation. So it's not delivering on this notion that we think that markets look more cautious sometimes than other times. Uncertainty prices are bigger sometimes than other times. And so part of the aim here is to see how we can get at those type of phenomenon. So I'm going to write down a baseline model. I'm going to put sets of, and where we're going to deviate from our previous work is I'm going to put sets of parametric models on the table that I want to allow for, as well as I want to allow them to be misspecified. And I'll kind of show you how I'm going to do that. My favorite way to think about distances between models is not the most tractable one. It's Chernoff entropy. But we're still going to use it, even though, and I'll show you how. And I'll show you how we're going to use it. I'll define it for you and indicate why I like it. We're going to be using some other construction, and then we'll want to compare the two. And the key thing is to say, how can these concerns about misspecification alter market prices of uncertainty? Can we get something that delivers variation in those without putting it in from the outside? So there's a sense in which Campbell-Cochran's model delivers it from the inside through some fundamentally and somewhat funky nonlinearities. So here we want to also deliver it from the inside. The other way it's done extensively in macroeconomics and also for recursive utility models is it comes from the outside. We impose stochastic volatility. Macro models these days, they write down 10 primitive shocks and 10 stochastic volatility shocks, or whatever the number is, with like 20 shocks to play with and the like. And it's nice to see if we can't deliver some of that variation. I believe stochastic volatility is important, but it's nice to see if we can't get some of that variation from inside the analysis, and not just have to stick it all on stochastic volatility. So that's where we're headed. So I'm going to look at a really simple model here. It's going to be a really simple model for log consumption, and I'm going to kind of in order to take things out for a spin. Before I put in 5 other or 10 other bells and whistles, I want to understand how this mechanism works. So this isn't going to be the usual empirical asset pricing paper where you write down 15 moments, you write down 12 parameters, and you hit the 15 moments. We're not going to be doing that. I think that's interesting to do, but not at this stage. I want to understand how the mechanism works. And by design, I want it to be like usable and tractable and the like. It's easy to invent problems in this class that are not solvable. And so the outcome is going to be evidence of tractability is that we're going to get a stochastic discount factor that's a quadratic function of a growth state. In that sense, it's going to be very much Ang-Piasetti-like in terms of the output. And we're going to also be able to show a mechanism by which these uncertainty prices are high when a macro growth state is low. So there'll be an aspect of kind of price of this countercyclical uncertainty prices. They're going to, which in good times they're lower, than bad times they're higher. And that's what I want to get out of it, and I want to explain how. So that's the game plan. Cast of characters, baseline model, and then I'm going to write down some parametric alternatives. Okay. Then I'm going to use, as is very convenient mathematically, these positive martingales to represent alternative probabilities. I'm going to put convex sets of these martingales. I'm going to construct them. And then I'm going to look at, I'm going to try to build sets using notions of statistical discrimination or statistical discrepancy. And I'm going to focus on 2 of these. One's going to be Chernoff entropy, but the other one's going to be some variant of so-called relative entropy. Here's some references. I could double these. Let's get started. I promised you a simple model. This is it. It's not very, this is purposely unambitious. It's going to be rich enough to get at an aspect of something that Bonzo and Yaron talk about in terms of long-term risk. Now, long-term risk is an interesting subject in the sense of my own view is the primitive evidence for it in the macro consumption data is weak. You can find it if you work hard. It's not overwhelming. It's weak. Most of the evidence, the places where you find it showing up prominently is when you ask simultaneously for it to explain asset prices. So it's kind of, but the primitive macro evidence for it is weak, and we want to allow for it to be weak. Right? That's part of what the aim is here. Now, there are some papers that would claim otherwise. There's a recent paper by Shorfidi, Yaron, and Song that would suggest that there's some primitive evidence that make it stronger. But I'm still a little bit of a skeptic. But anyway, let me. So I'm going to write down the simplified version. I'm going to close out stochastic volatility on purpose because I want to generate the volatility endogenously. Of course, we can add on stochastic volatility. I'm fine with that, but I want to see what I can get without it. Okay? So this is a model where there's going to be a single state variable, xt. It's going to behave as it's convenient for me to do this in continuous time, but it's not. There's no subtleties of continuous time that are going to be really critical to this. This could behave like a first-order autoregression under this baseline model. Okay? Consumption itself, then, so we think of x as the growth rate in consumption, and then mu hat is just kind of the overall mean growth rate in that consumption. Okay? So I've kind of designed, but by construction, the x here has mean 0 when phi hat is 0. And in my baseline model, in fact, that's what's going to happen. Phi hat's going to be 0. Now, by going to continuous time, this is kind of a virtue and a liability. Issues about the sigma and alpha are off the table. Now, there's a recent set of probability work that's been done by Peng looking at whole ambiguous counterparts to Brownian motion that can get around this, throwing out certain aspects of absolute continuity and changing the game here, but I'm going to abstract from that now. So all the action is going to be in this stuff. Phi could be wrong, kappa wrong, mu wrong, beta wrong. They could be wrong in a variety of ways. Conditional means here can be off. I'm going to write down this model of conditional means, but I want to allow for other ones. And so so-called long-run risk is what comes out of this X process. So I have to have a nice, convenient way to build models, alternative probabilities. So I want to be assigned different probabilities to this underlying Brownian motion. Right now it says, dw is a bivariate Brownian motion with 0 drift. I want to allow there to be other stuff, other probability specifications. For that, I want to use martingales. Okay, so the ZT is this usual martingale construction. I'm going to have a vector HT, can depend on date T stuff, dotted in with the Brownian increment. I'm going to offset it, so this has this term here, the so-called conditional Jensen's inequality correction, and that makes this thing here a martingale under some additional side restrictions. Okay. So this means that I write down an H process here. I can parameterize these alternative probabilities by alternative specifications of H. Okay? And we kind of know from so-called Gersonov's theorem what that H does in this type of specification is it's like changing the evolution of that W from being a standard Brownian motion to being a Brownian motion with a drift HT. So it's changing the probability in a way that's tractable. Now, if I start appending drifts onto the Brownian motion, and they're state dependent, that's going to do things like it's going to change conditional means. And so it can be interpreted as parameter shifts and the like. Right? So from the martingales of probabilities, think of BT as just some bounded random variable in the date T information set. I multiply it by ZT, form the conditional expectation. So I've used here a form of so-called absolute continuity in the sense of sets of measure 0 over finite intervals that are all agreeing. So this is what I said is a corresponding, under that change of measure EH, that's how W evolves. Okay, so I've changed the probability. Under the changed probability, then I can think of this as this as being a Brownian motion with drift HT. So that's where the simplicity of continuous time comes in. If this were discrete time, then the changes would be a little different and a little bit more general. Okay? This would be kind of usual stuff. So now let me just start with a parametric alternative. Okay? So I'm going to start off by announcing a bunch of parameters. And now I'm going to change the parameters. Okay? I already see one typo here. That top equation needs to have a beta in front of the xt there. It's going to play a role in the analysis. But I'm going to basically have 4 parameters I'm going to play with: mu, phi, beta, and kappa. And think of beta as that thing multiplying xt. Okay. I'm going to begin with some baseline parameters. I want to allow for them at least these type of changes in the parameters. Okay? By changing these parameters, it's just like making a state-dependent move in that HT of a very particular form, and so it's just like writing down HT like this, linear in X. Okay? That changes parameters, and I solve this equation that tells me what the etas have to be in order to support that type of that type of change. So at the very least, I want to allow for models that allow these type of changes. So I want to allow for there to be unknown parameters. Okay? I want to go beyond just being unknown parameters. I would imagine I want to potentially also allow for parameters that might vary over time, that they don't have to be the same ones every time period. Okay? Now, once I allow for them to vary over time, then in general, what you want to do to fill out a complete probability specification is start putting in processes over those and the like. And I want to kind of allow them to vary without having to tell you exactly how they're going to vary. So that's going to also be on the table. Okay. Now, how we can go forward here? There's different ways to go. And we're going to do one thing, and other people have done other things. So one possibility is at this point in time, we just literally take that H and we just restrict it directly in terms of magnitude. And that's the kind of, this is, if you read Chen and Epstein's paper from 2000, that's essentially what they're proposing to do. So we could kind of restrict that instant by instant. Okay? We're instead going to appeal to construct neighborhoods by using statistical measures of discrepancy. So that's going to allow, that's going to push us in a little bit different direction than the Chen and Epstein direction. It's going to basically force us to be thinking, make us think about intertemporal neighborhoods of parametric alternatives. So we want to put these parametric models on the table, but we want to allow them to be misspecified, so we're going to also put in other models on the table that are statistically close to those. Okay. So how do you build a statistical discrepancy? It's really easy. You could probably get one named after you if you're really clever. What you do is you write down a convex function. Okay? You write down a convex function. I'm writing down such a function f here. If you kind of ignore that part of it, this is going to be a convex function. This has this. Of course, this is wrong. It's supposed to be 0, typo. It's supposed to be 0 there. Okay. It's going to be 0 at 1. It's going to be strictly convex. That martingale that I'm used for a change of measure is going to have expectation 1. So by Jensen's inequality, I start taking expectations of these things. I'm going to get things that when the probability is exactly 1, I get 0 out. If it deviates from 1 but has expectation 1, then it's going to give positive numbers for the expectations by Jensen's inequality. So like if you leave that part out right there, you have a set of discrepancy measure that statisticians attribute to Reed and Cressy as a mode of, as kind of ways to test distributions. There's a bunch of special cases. Set R equal to 1, you get a quadratic measure. I guess that goes all the way back to Carl Pearson. You set R equal to -1, you get the expected log likelihood ratio as the negative log likelihood ratio as your criterion. The one that we're going to use is R equal to 0, which is particularly convenient. And that by L'Hopital's rule, you just verify as z log z. But we're going to be interested in others. Now, when you build these discrepancy measures, they are discrepancy. That is the fact that you're talking about a measure of discrepancy between two models. But it's not like typically a distance where if you flip the two different orders, you'll get the same thing. So kind of what you call the baseline and what you call the alternative. In general matters, except in special cases. So now our previous work stopped here. I'm going to do something, and this is in order that I can include these parametric models very easily, put in a tilt in here. It's going to stay a nice convex function. It's still going to be 0 at 0. So it's going to have all the nice properties of a statistical discrepancy. But it's going to take this function here and tilt it a little bit. And as we'll see, by doing this tilting, it's going to be very easy for me to build in these parametric alternatives and make sure that they stay inside my neighborhoods. So that's going to be the role of this thing. And then there'll be a special choice of zeta that's going to kind of do the work for us. So statistical discrepancy is basically all about making up these f functions. Now we want the dynamic counterpart to this. And we want to apply this to martingales. So this martingale is going to be this entire process, and we're going to build a statistical discrepancy. We're going to have to do two things. We're going to have to average over time. We're going to have a subjective discount rate in our decision problem, and I'm going to use the same one here. Okay. And I'm also going to build some other process here. I'm going to take the C tilde process. We'll see what that is in just a minute. I'm going to integrate it from 0 to t. Okay. I'm going to build my discrepancy measure then as that the F tilde I had on the board before, Z the martingale at date t. This is that zeta function is going to show up right here. That parameter is going to show up here. And then I'm going to look over all periods. Right? These are processes that there's could be no nice limit of z which is going to allow me to do the change of measure. So I have to keep track of the entire process here to make it work. And I'm going to discount things here. And the discount is going to be important. So, and this is consistent with our other work, so I'm going to compute this. Okay. Now it's handy to just do simple integration by parts. If I do integration by parts off of this formula here, using the family discrepancies I talked about before, if you trust me, it's just going to be this. I'm going to be the martingale raised to the power r minus 1. I'm going to take the norm now of this ht squared. At squared, right, the h's were those kind of drift distortions connected to Gersinoff theorem. I'll put the squares there and compute that. So that's just integration by parts. And then I've got this other term that's going to show up that's going to do this. Right? Where this is now what was used in this, it's that little zeta term here that's used there. Okay. Now notice what happens here when r is equal to 0. This is linear in z. Of course, this term here is linear in z. The zh is going to be also how I change the objective function of the decision maker. So everything in sight becomes linear in z when r is equal to 0. Other choices of r, one has to bring along additional state variables like this whole martingale and everything. But it scales out in a very simple fashion when r is equal to 0. So for tractability reasons, r equal to 0 is the most convenient one. And that's the one that connects to relative entropy. We modified it by sticking on this piece here. Okay. Yes?
Is this going to be a way of kind of measuring just how far apart two processes are eventually going to drift in some sense? So is there, I mean, it seems as though that kind of, on some level, doesn't pay attention to what people have seen in the past. So is there any way to kind of talk, is that like the information that we have, when we think about like looking at the history of data that we've seen, and we estimate things and we kind of fit models?
So something that I think is, we've done, we've explored in other work, and I think would be interesting to combine with this, is a situation in which we really also put on the table active learning about different things from past data. In some sense, we put so many models on the table here. Yeah, I mean, here's a simple example. Suppose you have model A and model B, and you don't know what prior to put over it. If you put all possible priors over model A and model B, it includes point priors, and at the point priors, one never learns. So if you put a rich enough set of priors over families of models, you eventually get yourself in these situations in which you close down learning, and that's what's going on here. I think it's also very interesting to put on the table narrower sets of priors under which you could actually hope to learn from. But that's not here. So indeed, this isn't a measure of, you're right, this is more of a prospective measure looking forward about how close models could be with the notion that we've settled upon this baseline model because it's a good approximating model, and at this point in time we're going to give up trying to learn, trying to deviate away from it. And so the models we left on the table are ones that that we just think that were statistically hard to tell apart. But it's not based on feeding through past data to make that assessment.
So it seems like this is also saying that like on some level I don't have an opinion about where my model is most likely to be wrong.
Going forward, so what I'm divorcing here is the model could be wrong in the future in ways that aren't connected to the past. And I want to put that channel on top of it. Well, I have a view because I have to write down this set. So there's going to be a view, but it's all going to be captured by this set instead of by a much more structured thing. Yes.
And the vector X is observed completely by agents?
Yeah, right. This is a model. This is a model. We'll come back to that. This is a model where the state vector, the state variable x is observed, and that's important. Yeah.
So the tilt is what's going to give you the time dependence that you showed before?
The tilt's going to give us an easy way to make sure parametric models. So I can build a big neighborhood of models, and I may leave out the parametric models I care about, but it'd still be big in some other sense. And that was the danger in our other stuff. How could we make them big enough on the one hand to contain parametric models that interest us, and the other hand put a bunch of other stuff too? So we want to accomplish both here. And this tilt's going to give us an easy way to do that. Okay? Okay, so I showed you how to define that set big delta of martingales. If I make it less than or equal to that, so the threshold also involves the psi tilde, but this is the expectation under the baseline model. There's no model distortion here. This is computed under the original probability model. If I use that as the comparison point, then if H's satisfy this restriction, they're necessarily in that set. Because now you've got a kind of a point-by-point inequality and you're averaging over a bunch of stuff. So you're guaranteed by introducing this, you're guaranteed to have models of this type inside the set, plus a bunch of other stuff that is arguably statistically close to those models. Okay, and you can satisfy this with time-varying parameter models. In our implementation, this is going to be a quadratic function of x, and it's going to allow for things like changing the autoregressive coefficients and the like. Because all the changes, remember, the drift distortions we cared about were all linear in x. So the C here is going to be quadratic in x. So as tilt is what was missing in our earlier work. It's going to be a way to kind of guarantee that in our construction we include all these parametric models. Okay, so I talked about this. Now I'm going to use this as the set I'm going to use to pose a recursive decision problem. Okay, I'm going to write even though this is an endowment economy, a so-called planner's problem is useful because it allows you to figure out decentralized prices. Basically, you take the planner's problem to figure out what the planner views as a so-called worst-case model. Then those things show up as the corresponding uncertainty prices. Then you can go back and decentralize, write down a portfolio problem, and verify the prices and everything else. So the planner's problem, you can write down a Hamilton-Jacobi-Bellman equation. I propose you trust that this is the correct one. The theta is the multiplier off the constraint. That's the additional term coming into it. Okay. The implied stochastic discount factor is going to be of this form. I'm going to produce an H, which is going to turn out to be linear in the state. This is going to be the type of, this is going to look very much Ang-Piazzesi-like. There's going to be an H star here going with the DWT, and that's going to give rise to the worst case model is going to give rise to this something which is going to be affine in the state x, a constant plus an x. And that's going to have a direct interpretation as changing those parameters. So the worst case models, even though we allow for a bunch of other stuff, is going to be inside that parametric class that I talked about before. And we'll be computing those. Then this would be the usual kind of risk price. If we had closed down this channel, this is what we're getting out of the uncertainty price. This part, of course, is invariant. This part here is going to be, and we're just doing this under log utility for simplicity. So I propose you trust us that we can solve the Hamilton-Jacobi-Bellman equation. It's exponential quadratic. It's not clear I can, but I got RAs that know how to use Mathematica. So anyway. Okay. So loading in this tilt to the zeta tilde is going to affect the uncertainty here. And a quadratic C tilde is going to give this kind of quadratic log stochastic discount factor. Okay, so that's not my favorite discrepancy, conceptually. If I had to, so I'm going to tell you one I like better. This is going to get rid of Stavros's discounting, so he'll be happy. Okay, and then what I want to do is then compare whether I can solve it under one, and then I can look at the neighborhoods I get out of that and compare it to one if I change the neighborhood construction. Okay, so I think it's handy to have something that's a distance, not a discrepancy. And I think it's handy to have something that has a nice simple interpretation for it. So we're going to go back to work of Chernoff, extended in a dynamic setup. Okay? So let's imagine I've got a baseline model, and let's imagine I've got some other alternative model. Okay? And I'll just announce them. Maybe it's in this parametric class, 2 models. You're a decision maker. You have a simple job. You look at data, and you got to pick one that's right. Okay? Now, of course, we know from the standard hypothesis testing that you make type 1 errors and type 2 errors. I can never remember which is which, but one's rejecting the null when you shouldn't, the other's rejecting the alternative when you shouldn't. I want to like dispense with the null and alternative. I'll just kind of call two models. So I'm going to make two one calls type 1 and one is type 2. Now, what's going to happen as you increase the sample size? As you increase the sample size, errors are going to diminish. Now, classical statisticians, for entirely unusual reasons, used to keep type 1s fixed and drive type 2s to 0, or for whatever reason. Then they got more clever and started making models drift to each other to get around that bind. But anyway, we're not going to do that. We're going to allow both to collapse to 0. And if you do a max-min decision-making, if you do Bayesian decision-making with priors over the two models, what happens is you're going to make those error probabilities go to 0, both of them. Okay? And how you weight them may change based on priors or min-max or whatever. But the things that will be the case is the decay rates will be the same. So how fast those probabilities eventually go to 0 of type 1 and type 2 errors gets equated. If they go to 0 very, very slowly, I'm going to call those models hard to tell apart. If they go very, very fast, those are models that are easy to tell apart. So we're going to literally compute these decay rates. Okay, so that's, and so a Chernoff notion of a distance of discrepancy between models maps into what's the decay rate that comes out of this, the common decay rate that comes out of this. Okay? And it ends up being symmetric, and it has interpretation back to this problem. Okay, so you can actually, there's ways to do this using so-called large deviation analysis. And I propose you trust me. You want to solve this problem. You want to take the ZTH and, there's this issue of what power R you raise it to. Well, look across all R's and kind of take the log of this 1 over t and optimize over the R's, and that gives you the bound. It's kind of remarkable this works, but that large deviation theory is kind of beautiful stuff, and so I won't go into this, but there's this calculation you do. There's no discounting here, so Stavros is concerned about discounting. It's off the table. You're just looking at, okay. So these models you can tell apart, but ones under which the Chernoff entropy is tiny, it would take a ton of data. So this is an issue about does it take 1,000,000 years to tell them apart or just a decade? It's supposed to make those type of distinctions. And these are all kind of ex-ante distinctions. So this isn't looking at historical data. It's those ex-ante distinctions. So I could build neighborhoods with this. Okay? And so what the paper does is we have these plots. We compare the set of models done my way that I described previously with relative entropy tilting and this. And we show how similar they are over all the relevant ranges. And we do direct comparisons of them. And so they're not identical, but there's some similar flavors to them. I'm not going to get into that here, but I just want to show that connection's there. At the end of the day, we are, though, going to calibrate using Chernoff entropy. We're going to announce half-lives. That's going to tell us how big this overall neighborhood is, and then we'll do the comparison between the worst-case model and the baseline model. So let me go back a slide here, a couple slides. I'm going to take this term here and just specify it up to scale. I'm going to pick that scale parameter to match half-lives off Chernoff entropies. Okay, so I'm going to take this out to spin in two ways. All right? They both kind of have antecedents in the literature, and I'll simplify both models. So I'm going to do Bonzo-Yaron without stochastic volatility. Now this gets back to Larry's question. This analysis, Bonzo-Yaron's analysis, all presumes that the economic agents know this growth state. This model is estimated without knowing the growth state. So the econometrician doesn't observe it, economic agents do. We're going to fit quarterly data to it. We don't. Bonzo-Yaron get like incredible persistence in this growth factor. We don't. We get persistence. It's not precisely measured, but we're going to use what we get out of the macro data. It's going to treat this state variable as hidden to the econometrician, but not to investors. There's another work that I'm also familiar with that we fit a VAR-style data, and instead of treating this growth state as unobservable, we try to use macro data to try to pin down the long-term risk components. So we use business-related earnings here. I think here it's like corporate corporate profits and proprietary income. To get anything, we have to use a broader measure than actually in the Hansen, Heat, and Lee literature. This evidence is not like, this is fragile evidence, but that's the whole point of this exercise. How do decision makers confront fragile evidence? But anyway, so we also fit this. Okay. Now to get back to the parametric class, this is a vector auto regression, like 4 legs and everything. Just to keep things simple, we're going to actually fit. We're going to produce a kind of counterpart Bonzel-Yaron type model or long-run risk type model that captures the same features. And we go through exactly how we do this in the paper. Now in the Bonzel-Yaron model, there's a shock to consumption and a shock to the growth rate of consumption, and they're uncorrelated. That's corresponding to alpha dot sigma 0. God knows why, I don't know, it just is, just assumed. If we want to match this to what Hansen, Heaton, and Lee do, we have to allow correlation. So there's going to be a difference that's going to matter for us actually quite a bit is that the shock to consumption and the growth rate shock have to be correlated to have any hopes of approximating this exercise. And that matters. Okay? So this one here, effectively this state variable is revealed by data. This one to the econometrician, that one is not. That one, there's things that are uncorrelated. This one, they have to be uncorrelated. They're uncorrelated there. They have to be correlated here, and this correlation is important. Okay, so this is the first one. We just fit it to consumption data. Right? There's our autoregressive parameter. Okay, this is in continuous time, so 1 minus that is the autoregressive coefficient. It's not the usual Bonzel-Yaron 0.999 or however many nines they want to put, depending on the paper. But this is the one that we get out of the data, so we use this. Okay. Beta, we essentially normalize that to 1 here in the original model. Under the alternative models, it will change. Phi, that's the mean of the growth state. Now we've already got a direct mean in consumption, so in some sense it's a freebie to 0 this side as well initially. Okay. So now what we want to do is we want to load in these different half-lives. A half-life of 40 means that you put a lot of models in the table. A half-life of 120 observations, that's how many observations it takes to chop in half the type 1 and type 2 error probabilities. That one, it means that you've got a lot fewer models in the table. Okay? So we're using Chernoff entropy to do all these calculations here. How do we scale that quadratic function? Okay? Now the quadratic function we use is this. If I set that quadratic function to a constant, it would have been just like our earlier work. And then we know the outcome, all the distortions are constant. So we thought, to go kind of the polar opposite case, we loaded up all into x squared. So that means you're focusing, these parametric alternatives we initially entertain are all ones and change to the autoregressive coefficient kappa. Those are the ones we load in to make sure they're viable. We allow for other ones. And so what happens is you move kappa some, but then you still continue to distort this and this. So you're taking these means and distorting them. Without this term, or if this were 1 or a constant as implicitly in our previous work, there would be only these 2 columns and this would just stay constant. Now what's happening is you're also distorting this. One could load all the distortions in here as this parametric alternative asks, but you're still going to choose to distort these guys. In some sense, what the decision maker fears is misspecifications that have long-run consequences. These invariant, shifting things invariantly for the future in a bad way is the thing that has the biggest utility consequences. Okay, so if then once you put on this, we kind of make these things more feasible, and then you start pushing this as well. So arguably, so there's debates on this. One is, do you want to look at the worst case model and ask ex post whether you think it's interesting or not? There's a whole literature on robust Bayesian stuff that was initiated by I would say by DiFinetti and Savage, and much to many people's surprise, saying that, well, we don't know priors exactly, and when I do prior sensitivity analysis, then Good kind of makes these arguments. So if we're doing prior sensitivity analysis and doing min-max stuff, maybe we ought to look ex post at the priors and see how reasonable they are. So someone could say I should look ex post at these parameter values and see how reasonable they are. Perhaps this long run response here, this being negative, that the worst case long run growth rate adjusting to both these contributions becomes negative, makes you a little bit more suspicious of this one. But stuff maybe 40 starts looking a little fishy. But one could also argue that looking at the worst case models is not the right way to think about the plausibility of this apparatus. I could say more about that, but not now. So here's like this is like the implied model for how consumption growth rate, how consumption behaves over different horizons under the two different models. These are like the 0.1 and 0.9 interdecile ranges. That's under the original baseline model, and then you're tilting it downwards, and that's given by this plot right here. Yeah, quarterly. Yeah, quarterly. So that's how you're thinking about consumption going forward, and then you're making this conservative adjustment by shifting things down. You're cranking up the persistence, but you're also shifting those constants. So here are the uncertainty prices. Now, I like to think about uncertainty prices as having a horizon impact to them. And at this sort of power utility, you would see more interesting notions of the horizon impact. That's given by here. I have a shock tomorrow. The shock tomorrow affects a payoff, say consumption in the future, and therefore it has an effect on any prices to claims to consumption in the future. That's a sense in which there's like trajectories here. These are like pricing counterparts to impulse response functions. They're flat, so you don't have to. And that's typical in recursive utility with high risk aversion. It's typical in this setup here as well. So they're flat. So the horizon dependence isn't the important thing. The interesting thing is how much variation you're inducing here. Okay, so so what's going on here is these are the plots for the different half-lives. The blue circles are the case in which I'd closed out. I instead of making that quadratic, I make that thing one like in our earlier work. In that case, you get no variation, and you just get a straight line. Okay? As you come down, you're going to increase the variation here, and you're going to shift up the level a little bit, and you're going to increase the variation a lot here. And that's and these are the interdecile ranges of the prices moving here, and they're moving kind of in a countercyclical way because they're connected to this growth state in a negative fashion. So as you allow more models on the table, then you're increasing the variation in these uncertainty prices. I've loaded it here, kind of making the maximal impact by loading these C's to be proportional only to x squared with no constant term. One can, of course, go between this whole red band and that blue line by just changing how you construct the original baseline C. So the red points are kind of the medians of these prices, and these are kind of in units of Sharpe ratios. Then this is how much they're fluctuating. So you can get dramatic fluctuations out of this. I think this is probably way too much. I just want to show how much you get out by loading as much as possible into that term there. Obviously, the blue line is way too little, so you can go in between. So is it clear what this is? If it's not, this is one of the punchlines. So if you don't understand this, I should just pack up my bags and close it up. But anyway.
So they're choosing a worst case. They have a single worst case model that they've come up with. Are they and that model has different drift. And so you might imagine that so is it going to be the case? I guess I would have thought that when that x is low, that high drift is particularly bad, but when x is really high, faster mean reversion starts to look bad.
Right. So that feature showed up in some of our other work with learning. But so what goes on here is the fact. Let me just go back to this table here. So this is like this mu plus beta phi over kappa is kind of a notion of a long run mean to things. And so I'm doing a shift here. This depends on the inverse of kappa. If I lower kappa here, I'm going to crank that thing up. So moving kappa down is going to make this kind of the long-term consequences of this very important. And so in this setup, it's the case that you want to shrink kappa. There's a mechanism we talked about in our earlier work, which I'll get to in the conclusion, which is more along the lines of what you talked about, and I can talk about how to get that mechanism there here. But here's what's operating in here. It's the fact that if you start doing a shift in this guy, it's going to play out over time and in ways that are going to interact with the kappa term. And a smaller kappa is going to give it a more dramatic impact. Okay, so Suppose now we do it, this calibration connected to Hansen, Heat, and Lee, but we allow, and we specifically allow for this, we have to allow for this correlation between the consumption shock and the growth shock, closed down in the Bonsley-Aron model. And this starts to matter. First of all, the beta matters here. So beta is this, consumption depends on X, okay? Under the baseline it's 1. Under the worst case models, it starts becoming, consumption becomes a little bit more predictable. This coefficient starts increasing on you. This channel is closed down because of the lack of correlation. You open up the correlation, you open up this channel. Okay. Now, if I look, something that I should have made clear in this previous plot, these are the prices for consumption shock. That's the price for the growth rate to consumption. Okay. The growth rate to consumption shock here tends to be bigger, and that's typically the case in those models. This is the case, but once I introduce this dependence, so it's going to change on us. So now I've got two shocks. One shock hits consumption and the growth rate, and the other one hits only the growth rate alone. If I square shocks that way, then the first shock becomes much more important. Okay. And again, so I'm sorry to flip back and forth here. This thing gets kind of nutty at 40. Once I see numbers like that, I would say this looks like crazy stuff. Like I've just endowed this guy with potentially crazy beliefs. Okay, so I think this is why I think it's interesting to look at the implied worst case model, see how stupid it looks. Yes?
Is there a way within this construction to kind of say, maybe I think I know the long run mean with more precision relative to the predictability and consumption over a given period of time, so you can kind of fix the last column or restrict that more, but play with the kappa?
So one could do that, but statistics would suggest just the opposite, that it's that long run means are very, very hard to estimate. So I have to think about how to do that, but I think I'd almost want to push the opposite thing. But, so anyway, the 40 I think starts looking a bit nutty here. But anyway, so activate this new change, and that is how much predictability there is in consumption coming to that beta coefficient. It matters. It shows a role, and also it makes this partitioning of prices across shocks look quite different. Not surprisingly, because we're now introducing correlation. Again, the blue lines are if we closed it, if we close things down to not allow for this the state dependence in the XC function. And again, this is a lot of variation. That's no variation. By going in between, you start loading in these C's that have both constant terms and quadratic terms. We just went to the extreme to see how much volatility we could get, and you can get a substantial amount this way. Okay, so concluding, we're using tilted discounted relative entropy to pose the problem. We use Chernoff entropy to calibrate. We allow for time-varying parameter models and other statistically similar ones. And this is a way to get large uncertainty prices when growth prospects are weaker. Now, we can complicate this, and it's potentially interesting to do this. Stochastic volatility, I think, is interesting in its own right. It's hard to measure the persistence of stochastic volatility typically, so maybe that's where we ought to be throwing a lot of the concerns about uncertainty. Right now, we've got Ang-Piasetti we're kind of a restricted version of Ang-Piasetti, so in some sense, I guess one could try studying this as to what extent we've imposed interesting restrictions on their setup. But they just impose it directly as kind of a reduced form notion, and we're trying to give a structural interpretation of it. Impose social externalities in the form of habit persistence. We know that Campbell Cochran have done that. Now, I was asked this other question about the robust learning, and that channel also gets time variation, but in a different way. That one has explicit learning on the table. I've got a model with a lot of persistence and a model with less persistence, and I don't quite know how to weight them. I've got a family of different initial priors and posteriors, and then the question is how I twist them. And in that case, it's the case that when there's good histories of consumption, you want to let the good times roll, so the bad model is low persistence, and when you get a history of when you get a bad history of consumption, then you fear persistence, and the worst case model becomes the one with more persistence. So there is a shifting over time of this autoregressive coefficient in the worst case model through this learning channel. So it's a different channel, but it also gets time variation, and it's more along the lines you were suggesting. Oops, I guess we're over. Any more questions?
So if I think about the cross-section of people,
Yeah.
and just going back to this, the effect of the period utility function on the
Yeah.
set of models, it
Yeah.
would seem that if people are more risk averse, they entertain larger sets, and so we have a, is that right?
If people are more risk averse, we do what?
And the parameter ranges become bigger. 'Cause
If they're more risk, if they're, so it'd be still connecting by turn-off entropy, so it's kind of a trade-off where they stick the misspecification. If I put in curvature in the utility function, the question, would I want to pay even more attention to the autoregressive parameter? I don't know the answer to that. That's a good question. I think it'd be interesting to
one can
explore.
sort of figure it out also in a simple example, because there is,
Yeah.
so experimental
Yeah.
people look at this, right? They have these things of risk aversion versus ambiguity aversion, they
Yeah.
go together in the cross-section and so on. And this connects to this somehow, because the
Yeah,
size
so-
of the belief set has to do with curvature.
So I'm not sure what happens there. I think it'd be interesting to explore. We haven't done it, but it'd be interesting to explore to see what happens, how that works.
All right, let's have